Good day to each and everyone. My name is ELMON ALCARAZ from Bachelor of Science in Civil Engineering, and what I'm going to report right now is the three methods for indirect method. The first is the Blaney Criddle method, the Jensen Halsey method, and the Hargreaves method. First, we are going to report the first method, which is the Blaney Criddle method. The Blaney Criddle expresses the consumptive use or the evaporation in terms of temperature and daytime hours. The modified equation by the SCS is given as E sub P is equal to 2.54 kF, where F is equal to the summation of P sub H times P sub F divided by 100, where your E sub P is the PET, or the potential evaporation in a crop season in centimeter, where your K is an empirical coefficient, depends on the type of the crop and stage of growth, where your F is the sum of monthly consumptive use factors for the period, where your P sub H is the monthly percent of annual daytime hours, depends on the latitude of the place, and your T sub F is the mean monthly temperature in degrees Fahrenheit. For simpler and easier explanation, the Blaney Criddle method is a straightforward way to estimate the amount of water plants need for irrigation requirements based on temperature and the length of the growing season. Here is a simplified explanation. For temperature factor, plants need more water when it's hotter. This method uses average temperature to help determine water needs. For growing season, the method considers the period when plants are actively growing. More water is required during this time. And for formula-based, the method uses a basic formula that combines these factors to estimate the water requirement. In essence, the Blaney Criddle method helps farmers and gardeners figure out how much to water their crops by looking at the average temperature and the growing season duration. So for our first problem, given the table from the month of November to February, for the month of November, our T sub F is 61.7 and our P sub H is 7.19. For the month of December, our T sub F is 55.4 and our P sub H is 7.15. For the month of January, our T sub F is equal to 51.8 and our P sub H is 7.30. And for the month of February, our T sub F is 58.1 and our P sub H is equal to 7.03. Given the formula P sub H times T sub F divided by 100, for the month of November, we will obtain 4.436. For the month of December, we will obtain 3.96. For the month of January, we will obtain 3.78. For the month of February, we will obtain 4.084. The summation of P sub H times T sub F divided by 100 is equals to F, which is 16.26. In finding the E sub E, the formula is 2.54 times K times F. Substituting the values, 2.54 times 0.65, which is the K for wet, times 16.26, which is the F, equal to 26.845. So for Jensen-Halsey method, based on energy balance equation, approximately 1,000 measurements of evapotranspiration over 35 years period at 20 locations in western US were made for this method or equation, where our equation is E times T sub O is equals to C times the quantity of T sub A minus T sub X times R sub S. And our climate data needed for it include solar radiation, our mean daily temperature and long-term mean maximum air temperature for the month of highest mean air temperature and elevation above sea level. The Jensen-Hayes from 1963 formula with adjusted unit reads E times T sub P is equal to 0.25 T sub A plus 0.08 times R sub S over 28.6, where our E times T sub P is the potential evapotranspiration rate, which have the units millimeter per day. For easier and clearer understanding, the Jensen-Hayes method is another way to estimate the water needs of crops, specifically focusing on the evaporation and the transpiration, or also known as the evapotranspiration, from the soil and plants. Here is a simplified explanation. For solar radiation, this method primarily uses solar radiation data. The idea is that more sunlight leads to more water evaporation and plant transpiration. For temperature, it also considers temperature. As water temperature rises, the water needs also increases. For evapotranspiration calculation, the method combines these factors into a formula to estimate the evapotranspiration rate, which tells how much water the plants, the soil lose. For adjustment for crop type, the different crops have different water needs, so the method includes factors to adjust the calculation based on the specific type of crop. In essence, the Jensen-Hayes method helps estimate how much water crops need by looking at how much solar energy they receive and the temperature, then adjusting for a specific crop type.
Given the formula for evapotranspiration, 0.025 times TA plus 0.08 times RS over 28.6. Given the data, TA is equal to 32.5 degrees Celsius and our R sub S is equal to 800 Li per day. Here is our solution. 0.025 times 32.5 plus 0.08 times 800 over 28.6. Just by substituting the data given, the obtained evapotranspiration is equal to 24.97 centimeter per day. Since the required unit for evapotranspiration is millimeter per day, we will multiply 24.97 by 10. And the final answer is 249.7 millimeter per day.
For our Hargreaves method, we have the formula PET is equal to 0.0023 times R sub A times T max minus T min times T min plus 17.8 over 2, where PET in millimeter per day is equal to potential evapotranspiration. Our R sub A is the mean extraterrestrial radiation in millimeter per day, which is function of latitude. Our Tmax is the maximum daily air temperature. Our Tmin is the minimum daily air temperature. And our Tmin is the average daily temperature. For clearer understanding, the Hargreaves method is a simple and widely used method for estimating potential evapotranspiration, or the PET, which is the amount of water that would evaporate and transpire if sufficient water was available. Here's a straightforward explanation. For temperature, this method primarily relies on temperature data, specifically the average, maximum and minimum temperatures. For solar radiation estimate, it indirectly estimates solar radiation based on temperature differences, assuming that larger temperature differences typically indicate more solar radiation. For the formula base, the method uses a formula that combines these temperature values to estimate evapotranspiration. In essence, the Hargreaves method helps estimate how much water plants need by using average, maximum, and minimum temperatures to infer the potential evaporation and transpiration. This makes it a practical tool, especially in regions with limited weather data.
Given the formula 0.0023 times R sub A times T max minus T minimum times the T average plus 17.8 over 2, our given data is our J is 35 and our phi is 25 degrees. However, for our estimation, here is our condition. Our R sub A is equal to 15.392 times D sub R times W sub S sine phi sine delta plus cosine phi cosine delta times sine W sub S. To find the value of D sub R is equal to 1 plus 0.033 times cosine 2 pi times J over 365. Substituting the value of J, D sub R is equal to 1 plus 0.033 times cosine 2 times 35 times pi over 365. Our D sub R is equal to 1.032. To get the value of our delta is equal to 0.409 sine 2 pi times J over 365 minus 1.405. By substituting the value of J, our delta is equal to 0.409 sine 2 pi times 35 over 365 minus 1.405. Equals negative 0.005. To get the value of our W sub S, our W sub S is equal to arc cosine times negative tangent phi tangent delta. By substituting the values, our W sub S is equal to arc cosine negative tangent 25 times pi over 180, since our phi is in degrees, times tangent negative 0.005. Our W sub S is equal to 89.99. Since we already obtained the value of our dr, which is 1.032, and the value of our delta, which is negative 0.005, and the value of our W sub S, which is 89.99, we can now obtain the value of our R sub A by substituting these values. 15.392 times 1.032 times 89.99 sine 25 times pi over 180 times sine negative 0.005 plus cosine 25 times pi over 180 times cosine negative 0.005 sine 89.99. Our R sub A is now equal to 15.88. Since we now obtained the value of our R sub A, we can now directly substitute it to the formula of 0.023 times R sub A times T max minus T minimum times T average plus 17.8 over 2. Our given T max is equal to 38 degrees Celsius and our T minimum is 29 degrees Celsius. So for our potential evapotranspiration, given 0.0023 times 15.88, which is our R sub A, times 38 minus 29 times 33.5 plus 17.8 times 0.5 our potential evapotranspiration is 8.43 millimeter per day.
That's all for today. Thank you for listening and I hope you gain insightful information.